Now, I shall start with module 2 of this chapter 1. This chapter consists of some fundamental results on completeness properties of a metric space. A remarkable result, rather known as remarkable theorem, namely Bayes category theorem, is presented in this module. I will start with module 2. The module 2 is dealt with some properties on metric spaces. Before going to start on some properties of metric spaces, we would like to define what is a metric space. Let X be a non-empty set. Show the Cartesian product x cross x of all ordered pairs x comma y, where x comma y belongs to x is also non-empty. The definition is like that: a function d colon x cross x to R means set of all reals is called a metric or a distance function over x if it satisfies the following conditions known as metric or distance axioms. D1, the first axiom, is dxy is greater or equals to 0 for all xy belonging to x, and dxy is equal to 0 if and only if x equal to y, and this property is known as property of non-negativity. The second axiom, D2, dxy is equal to dyx for all xy belonging to x. This property is known as symmetry. D3, dxz is less or equals to dxy plus dyz for all xy and z belonging to x. This property is known as triangle inequality. If D is a metric on X, then the pair XD is called a metric space. In a metric space XD, if x0 belonging to X and R is a positive real, we have the following definitions. Definition is that the subset X belonging to X such that dx naught x is less than R. The inequality is in strict sense of capital X denoted by BRx naught, which is called an open ball centered at x naught with radius is equal to R. As for example, if dxy is equal to modulus of x minus y for x comma y belonging to R, then Rd is a metric space, and for x0 belonging to R and for a positive real R, the open ball Brx naught is equal to x belonging to R such that modulus of x minus x naught is strictly less than R, which is equal to x belonging to R such that x naught minus R is strictly less than x, is strictly less than x naught plus R, and is equal to an open interval x naught minus R comma x naught plus R with midpoint x naught and of length is equal to 2R. Sometimes we write the open balls Brx naught by B first bracket x naught comma R first bracket closed. Similarly, if we define d dashed is equal to z comma w is equal to mod z minus w for any two complex numbers z comma w belonging to C, then CD is a metric space, full stop. The open ball centered at z naught belonging to C with radius is equal to R here R is a positive real, looks like an open circular disk. The metric D and D dash are called usual metric for R and C respectively, where R is the set of reals and C is the set of all complex numbers. The another definition is like that: the subset X belonging to capital X such that D x naught x is less or equals to R of a metric space X comma D is called a closed ball centered at x naught with radius is equal to R. The closed ball in a metric space capital X is generally denoted by BR third bracket x naught. Stop. The subset X belonging to capital X such that D x naught comma x is equal to R of a metric space X D is called a sphere centered at x naught with radius is equal to R. It is also called boundary, written as B suffix dr of open or closed ball centered at x naught having radius is equal to R. Note that the open balls in a metric space X D form a base for a topology called metric topology induced by the metric D on X. So, every metric space is a topological space with metric topology denoted by tau D. That is, a topology is induced by a metric D. We can also verify that the metric topology tau D is Hausdorff. Sometimes we say the topology is T2. Next definition is that a sequence Xn in capital XD is said to be convergent to an element x naught belonging to x if limit of n d x naught xn is equal to 0, or equivalently given any positive epsilon there is an index capital N is a natural number such that d x naught comma xr is strictly less than epsilon whenever n is greater or equals to capital N. If sequence xn is a convergent sequence in XD with x naught belonging to capital X and limit n d x naught comma xn is equal to 0, we write limit of n xn is equal to x naught belonging to x, and we see that x naught is unique in X since metric space capital X is Hausdorff. Sometimes we write limit of n x naught is equal to x naught as xn tends to x naught as n tends to infinity. Next, a sequence xn is said to be a Cauchy sequence in X if dxn comma xm tends to 0 as n comma m tends to infinity, or equivalently given any positive epsilon there is an index n generally taken as natural number capital N satisfying d xn comma xm is strictly less than epsilon whenever n comma m is greater or equals to capital N. It is easy to verify that in a metric space every convergent sequence is Cauchy, but converse is not true. Next definition, a metric space XD is said to be complete if every Cauchy sequence in X is convergent to an element of X. For example, the real number space R with usual metric dxy is equal to modulus of x minus y, where x comma y belongs to R is a complete metric space. This is what is known as Cauchy's general principle of convergence, and essentially by same reason the Euclidean n space Rn denoted as R to the power n consisting of all n tuples of reals like x equal to x1 comma x2 comma dot 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 comma xn, where xi belongs to R is also a complete metric space with usual called Euclidean metric for D, where dxy is equal to sigma I equal to 1 to n modulus of xi minus yi square to the power half, where x is taken as n tuples like x1 comma x2 comma dot 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 comma xn belongs to Rn, and y equal to y1 y2 comma dot 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 comma yn belongs to Rn. Similarly, we can see that the space of all complex numbers C and the Euclidean n space written as C to the power n consisting of all n tuples of complex numbers is a complete metric space with respect to the metric defined by d dash zw is equal to modulus of z minus w, where z comma w belonging to C and d dash z comma w is equal to sigma I equal to 1 to n modulus of zi minus wi squared to the power half, where z is equal to z1 comma z2 comma dot 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 zn belonging to Cn, and w is equal to w1 comma w2 dot 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 wn belonging to Cn, where the coordinates zi comma wi belongs to C, I runs from 1 2 dot 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 up to n. It is to be noted that number 1, the space of all sequences LP where P is restricted within 1 to infinity, P allows to take is equal to 1 is a complete metric space with respect to the metric D defined by dxy is equal to sigma I equal to 1 to infinity mod of xi I minus eta I whole to the power p whole to the power 1 by p, where x is taken as xi1 xi2 dot 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 xn dot 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 and y equal to eta 1 comma eta 2 comma dot 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 comma eta n dot 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 belongs to LP, where the coordinates xi I eta I belongs to R or in the set of all complex numbers. The second one is that the space of all real valued continuous functions over a closed interval a comma b denoted by CAB is a complete metric space with respect to a metric known as submetric D defined by df comma z is equal to supremum modulus of ft minus gt, where supremum is taken over the closed interval a comma b and f comma g are taken from CAB. So, this is an example of an incomplete metric space. So, the same space is considered here, that is CAB, collection of all real valued continuous functions over the closed interval AB, and we define another metric known as integral metric and is defined by df comma g is equal to integration a to b modulus of ft minus gt, where f comma g belongs to CAB and t belongs to a comma b. Without loss of generality, we shall prove for C01 because 01 closed interval is homeomorphic to closed interval a comma b. So, it is sufficient to prove over C01. So, consider the following figures, namely there are two figures, figure 1 and figure 2. See the figures very carefully. We see from the above figure 1 that sequence x and t is a sequence of real valued continuous functions over the closed interval 0, 1 given by x and t is equal to 0, where 0 is less or equals to t is less or equals to half and is equal to 1, where n is less or equals to t is less or equals to half, where n is equal to half plus 1 by n. Clearly, the functions xn in figure 1 form a Cauchy sequence because dxn, xm is the area of the triangle in figure 2. That means, for every epsilon greater than 0, dxm, xn is less than epsilon whenever m, n is strictly greater than 1 by epsilon. Now, we shall see that this Cauchy sequence does not converge in C01. So, define the functions x and t by xmt is equal to 0 if t belongs to closed interval 0, half and is equal to 1 if t belongs to closed interval am, 1 where am is equal to half plus 1 by m. We shall see that the sequence does not converge to an element. If possible, let xn converges to x as n tends to infinity, then for every x belongs to C01, we see that dxm, x is equal to integration 0 to 1 modulus of xmt minus xt dt. So, by triangle inequality is less or equals to 0 to half mod of xt dt plus integration half to am modulus of xmt minus xt dt plus integration am to 1 modulus of 1 minus xt dt. This inequation is named as equation number 1. Since the integrands on the right hand side of 1 are non-negative, so is each integral on the right hand side of 1. Hence, dxm, x tends to 0 as m tends to infinity would imply that each integral tends to 0, and since x is continuous, we should have xt is equal to 0 if t belongs to left closed 0, right open half, and xt is equal to 1 if t belongs to closed interval half, 1. This shows that x is not continuous 0, 1, a contradiction to our supposition, because we have told that xn converges to x where x is taken in C01. Hence, xm does not converge, that is, sequence xm does not have a limit in C01. Hence, C01 is not complete. As closed interval AB is homeomorphic to 0, 1 by the transformation x is equal to a into 1 minus t plus bt, where 0 is less or equals to t less or equals to 1, it follows that CAB is not complete. There are many examples of an incomplete metric spaces. Now, there is another definition, that is, a subset capital H of a metric space XD is said to be a nowhere dense set in X if interior of closure of H is equal to phi. Equivalently, for every open ball BXR or BRX, X is taken from X and R is a positive real, there exists an open ball Bx1, R1 subset of Bxr where x1 is taken from X and R1 is a positive real, such that Bx1 R1 is free from points of H, that is, Bx1 R1 intersection H is equal to phi. A metric space capital XD is said to be a set of first category if capital X can be expressed as a countable union of nowhere dense subsets in X. Otherwise, we say XD is a set of second category, that is, a metric space XD which is not a set of first category is called a second category. As for example, every finite set in a metric space XD is a set of first category. The solution looks like this. Let capital A is equal to finite set, say x1, x2, comma dot 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 comma xn is a subset of XD. Since each singleton xi where I is equal to 1 to up to n is nowhere dense in X, and as A is equal to union I equal to 1 to n xi, it follows that A is a set of first categories. Also, A is countable because every finite set is countable. Let capital Q is equal to R1, R2 dot 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 dot. This is a set where Ri's are rationals, and the metric on Q is defined as the same metric of R, that is a usual metric on R. Now, capital Q is countable and each Ri I equal to 1, 2 and so on is nowhere dense in R because every singleton set is nowhere dense. Also, Q is equal to union I equal to 1 to infinity Ri, so it is a set of first category. Just now we have finished with some examples of a complete metric space and incomplete metric space. Now, right now we will present a very remarkable result known as Bayes' category theorem, which characterizes the completeness property of a metric space. Someone says that it is a category theory, that is Bayes' category theorem is sometimes known as category theorem. Now, I will talk on an important theorem known as Bayes' category theorem. The statement of this theorem looks like this, that every complete metric space is not a set of first category, that is, every complete metric space is a set of second category. We shall prove this theorem by a method of contradiction, that is, if possible let the metric space XD be complete and be a set of first category. So, X can be expressed as a countable union of nowhere dense sets in X, that is, X is equal to union k equal to 1 to infinity E k, where E k's are nowhere dense sets in X. As E1 is nowhere dense in X, so we can find an open ball B x1 comma epsilon 1, where epsilon 1 is a positive real such that B x1 comma epsilon 1 intersection E1 is equal to phi. As E2 is nowhere dense in X, so we can find an open ball B x2 epsilon 2 where epsilon 2 is greater than 0 such that B x2 comma epsilon 2 subset of B x1 comma half epsilon, where epsilon 2 is less or equals to half epsilon, satisfying B x2 epsilon 2 intersection E2 is empty. As capital E3 is nowhere dense in X, we can find an open ball B x3 comma epsilon 3 subset of B x2 comma half epsilon 2, where epsilon 3 is less or equals to half epsilon 2 less or equals to 1 by 2 square epsilon 1 such that B x3 comma epsilon 3 intersection E3 is empty. Proceeding in this way, we can find a sequence of open balls B x n comma epsilon n, where epsilon n is a positive real with B x n comma epsilon n subset of B x n minus 1 comma half epsilon n minus 1 satisfying B x n comma epsilon n intersection E n is equal to phi. Thus, we have number 1 B x n comma epsilon n subset of B x n minus 1 comma half epsilon n minus 1, 2 B x n comma epsilon n intersection E n is equal to phi. Number 3 epsilon n is less or equals to half epsilon n minus 1 less or equals to 1 by 2 square epsilon n minus 2 less or equals to dot 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 less or equals to 1 by 2 to the power n minus 1 epsilon 1. Show that epsilon n tends to 0 as n tends to infinity. Now, we have open ball B x n plus 1 comma epsilon n plus 1 is within the set B x n comma half epsilon n, which is an open ball. Similarly, B x n plus 2 comma epsilon n plus 2 subset of B x n plus 1 comma half epsilon n plus 1 subset of B x n plus 1 comma epsilon n plus 1 subset of B x n comma half epsilon n. Thus, we see that for any positive integer p, B x n plus p comma epsilon n plus p is within the open ball B x n comma half epsilon n. Therefore, D x n plus p comma x n is less or equals to half epsilon n tends to 0 as n tends to infinity whenever p is taken as 1, 2 and so on. Thus, we see that sequence x n is a Cauchy sequence in X. As capital X is complete, let limit n tends to infinity x n is equal to xi belonging to X, say. But we have d x n plus p comma x n is less or equals to half epsilon n. As p tends to infinity, x n plus p goes to xi, and so d xi comma x n is less or equals to half epsilon n, which is perfectly less than epsilon n. So, xi belongs to open ball B x n comma epsilon n. That means, xi does not belongs to E n for all n. Therefore, x equal to union n equal to 1 to infinity E n, and xi does not belong into X, which is a contradiction. Therefore, capital X d is not a set of first category. That means, X d is a set of second category. Thus, we see that every complete metric space is not a set of first category. Thus, in module 2 of this chapter 1, what we have learned, that is the completeness property of a metric space, rather the characterization of completeness of a metric space. With this remarkable result, Bayes category theorem, we end this module.